All right. Okay, so then let me start again. Also, of course, welcome everybody here and happy World Logic Day. I'm Stefan Seider and I'm here with Agata Ciabattoni at the Vienna Center for Logic and Algorithms at the Technical University of Vienna in Austria. And together with Agata, we would cordially welcome you to our World Logic Day 2024 event. It was in 2019 when the UNESCO proclaimed the 14th of January the World Logic Day, because this day marks Kurt Gödel's day of death and Alfred Tarski's birthday. And then we started a couple of years ago here at UCLA with some activities around the World Logic Day. And among others, we every year have now this a talk by some prominent logician, an online talk, and we already had a couple of them. And this time the World Logic Day falls on a Sunday, and Sunday is sometimes inconvenient for people attending talks. So therefore we decided to do it 2 days earlier, so today on a Friday. Yeah, and so today it's my great honor to welcome and introduce Professor Adnan Darwiche as the World Logic Day speaker 2024. Adnan is the director of the Automated Reasoning Group at UCLA. And Adnan accomplished a lot of influential work on logic, probabilistic reasoning, knowledge compilation, and machine learning. So he's one of the few people who can show how one can put logic into action in a quite impressive way. I won't spend too much on describing Adnan's honors that he received a lot. So just very briefly, after his PhD from Stanford, he also got an honorary doctorate from the University of Artois, and he is a fellow of the AAAI, of the ACM, and the AAIA. Just briefly, I also want to mention that Adnan is also an award-winning educator. So he wrote an important textbook on Bayesian networks. And I also can highly recommend his online lectures on automated reasoning on YouTube. Many of my students, if they want to know something, I say, watch this lecture by Adnan on YouTube, then you know more about this. And now before Adnan starts with the lecture, just let me remind you that at the end of the lecture, we have a Q&A session. And please use the Q&A function on Zoom to type in your question. And you can also use this Q&A function to upvote questions of others. So you can already start writing your questions during the talk, because then at the end, we might already have a list of questions, some already upvoted, and then we can start with the question that most participants are interested in. If you are joining via YouTube, please go over and join us via the Zoom webinar. It's still, the registration is still possible now, and then you can ask your question. But without further ado, I now give the stage to Adnan Darwiche, and please join me welcoming him.
Thank you, Stefan, for the kind introduction, and thanks UCLA for the invitation to give this lecture on Logic Day. Let me share my screen so we can get started here. And let me see. Can you see my screen?
Yes, works.
Okay, very good, very good. All right, so I will start with some remarks on the title that I chose for this talk, and then some further remarks on what I would like to accomplish today. Now, if you look at the history of AI, the story we usually hear is that there have been multiple eras for this field. So from the very beginning, there was the logic era, which lasted for a few decades. And then around mid-80s came the era of probability and shortly after machine learning, and we now live in the era of neural networks. And within this narrative, the logic and its role, logic is cast as a tool for basically representing and reasoning with categorical beliefs. So we hear that logic is good for representing facts, while probability is good for representing uncertain beliefs, and it would be good to try to combine the two to get the best of the two worlds and so on. And the main theme of this talk is actually that this widely held perception about the role of logic as a tool for representing and reasoning categorical beliefs, and a perception that has been entrenched by major textbooks on AI. This perception is actually incomplete, and some would say outdated, because logic is actually two things. It is a calculus of truth and falsehood, which refers to this classical role that's usually attributed to AI, but it's also a calculus of events. And it's this second statement that I would like to make very sharp in this talk. In fact, if you look at what's been happening in AI over the last decade or two, as far as success stories that involve logic, that you'll find a lot of them actually have to do with this second role of logic as a calculus of events. And I hope this will be evident to you by the end of the talk. So another slide on perspective, because that will help me set the agenda for this presentation. So take an event like this. Susan exercises regularly and does not smoke. You bring in logic. It allows you to assert the truth or falsehood of this, and gives you a whole vast and sophisticated machinery for dealing with events, as we will see later. But you go to probability, and then you're able to say something maybe more refined, like this event has a probability of 70%. The key observation, though, even though I'm not talking about truth and falsehood, I'm talking about probability, the notion of an event is still there, because we're attributing the probability to an event. In fact, if you look at key probabilistic notions like independence or correlation, they're all between events. But as we will see, the mainstream literature on probabilistic reasoning deals only with the degenerate type of events that we will later define precisely and call simple events. The observations about probabilistic reasoning carry over to machine learning, because a lot of what happens in machine learning is actually based on probabilistic models. But there we find something also perhaps more profound, in the sense that if you look at the notion of a data set, which is the core notion in machine learning, the thing you learn from, the examples in the data sets are nothing but events. And again, we'll see that degenerate type of events. So the first part of the talk, about 60%, will focus on these two areas, and we'll see what happens when you bring logic as a calculus of events to bear on these two areas. And I can tell you what. One of the things you'll see is that the state-of-the-art systems today for probabilistic reasoning are, in fact, one of the outcomes of this endeavor. And we will quantify state-of-the-art precisely as we go on. The second part of the talk is about the area of explainable AI, which is something I've been active in the last 5 years or so. This is a vibrant area. There's a lot of work in this area now, particularly in explaining the decisions made by machine learning classifiers. And there we'll see that the core notions of an instance, which is the input to a classifier, the notion of a class, which is the output, the notion of a reason for a decision or an explanation for a decision, they're all events. And there again, we'll see what happens when we bring logic as a calculus of events to bear on this area. And I can promise you will be astounded. So let's wait and see. By the time we finish these two stories, the notion of logic as a calculus of event hopefully will be very clear, because we will see 4 very clear and distinct dimensions to this calculus. So let's get started. First, I want a couple of words on events so that we're all on the same page. I'm going to start by working in a Boolean setting where every variable has only 2 states, to keep things simple. Later, we'll have to operate in a discrete setting, because in the areas that I've mentioned, to do something practical, you need to work with discrete variables, variables that could have thousands and tens of thousands of values, but we'll keep this to the end. So here are 4 Boolean variables, L, K, P, A, and here are all of the different ways in which you can set their values. I have 16 of these. Each one of these is what we'll call an atomic event, what logicians like to call also a world or a possible world. And an event is simply a set of atomic events. So here's one event, here's another. And as we know in logic, logic gives us a way to specify events compactly. So this formula actually specifies this event. This means that P is true. This means that A is false. This represents disjunction. This represents conjunction. I'm using here engineering notation because it's more compact. And of course, the key thing about formulas is that you can have a compact formula that represents an event that is exponentially sized. And of course, this is also an event. When you take the set of all atomic events, that's the trivial event. Now, the notion of a simple event, which is going to be important here. If you look at the first three, these are all events, but they are simple, and this is not a simple event. What's the difference between these? The first three, each one of them can be specified using a formula of the following form, a conjunction of literals. So a literal is either a positive literal like this, that the variable P is true, or a negative literal like this, that the variable K is false. So all of these events can be specified by by conjunction of literals. This one cannot. You need an arbitrary formula for that. So simple events are ones that can be specified, as I said, by conjunction of literals, or what logicians like to call a term. Again, this distinction is going to be quite important later. I just need one more slide on basics before we get started. And that is a particular way for specifying events, which is known as negation normal form. These are formulas that we'll usually visualize using circuits. And the negation normal form, you start with literals and you build your formula using ands and ors. No restrictions on these ands and ors. So the only restriction here is you can only use negations with literals. You cannot have negations in the middle. This is, we'll see, is an influential way of representing events, and you'll see in the first set of slides, we will have a bunch of these popping up. So let's get started with the first area or the first part of the talk, which is probabilistic reasoning and machine learning. Here we're going to talk about probabilistic reasoning in the context of Bayesian networks, because you can do probabilistic reasoning in many contexts. We need to have a concrete context. And Bayesian networks have been pretty influential. In fact, a lot of discussions we're going to do in this context apply more broadly, but let's just do that. These are models that specify probability distributions. So here's a Bayesian network over 5 variables. It does specify distribution over these 5 variables. The key thing about these models is that they are compact representations of distributions. The distribution is exponential in the number of variables. The Bayesian network is not. You can do a lot of types of inference, but we're going to focus on the bread and butter, which is computing conditional probabilities like this, probability of one event given another. This is called the query. This is called an evidence. And if you're able to handle this query efficiently, you can do a lot. And people have been doing a lot with these models throughout the decades. The thing you need to know is that these models are constructed in different ways, either manually, like this one, and as people started initially, or they learned from data. And this is actually a very common mode of constructing these things, which is synthesis from other types of models, like probabilistic programs, probabilistic relational models. I've seen a lot of papers recently about quantum simulation. And models that are constructed in this third fashion tend to be the hardest. They're very large. This is an example of such a model constructed from a relational model. All right, now, before we get started, and to show you what happens when we bring logic as a calculus of events to bear on this computation and to lead to state-of-the-art systems, let me tell you what I mean by state-of-the-art systems. These techniques that I'm gonna try to summarize in a few slides to give you the main insights had their first peak in 2006, and they participated in the first UAI competition for inference. UAI is the main conference on probabilistic reasoning. And they were the only techniques that solved all benchmarks. And some of the benchmarks that they solved were thought to not be solvable at all. That was the first breakthrough. This is a while back. This is almost now. A couple of years ago, comprehensive evaluation by an independent group looked at 18 different methods for probabilistic inference. And what I'm going to talk about in the next few slides is the state of the art ACE is the system that embeds these techniques. And now we'll see what happened really and how logic did it. And not standard probabilistic techniques, but logic as a calculus of events. So there are two types of events that come up in probabilistic reasoning. There is the trivial event, which represents the probability space. And then there is a query that you want to compute the probability of. That's also an event. So what we really want to do when we want to compute the probabilities of event is effectively sum the probabilities of the corresponding atomic events. And in this case, it's this. So now we're going to see how we're going to do this. And we're going to do it in multiple stages. There are going to be like 3 or 4 insights that revolutionize this area of probabilistic reasoning. And let's go. But I have to tell you, the real major insight here is that we have to take events and structure them in a certain fashion based on what logic tells us, and that will make this computation happen efficiently. And I'm going to start by making an assumption that rarely holds, but it will get us going in the first step. That let's assume that all the variables in our distribution are independent. So if the probability of an atomic event is simply the probability of the literals that appear in that event. All right. So let's assume that for now. We'll relax it immediately after. Suppose now you have an event delta and you want to compute its probability. So here's what we're going to do. We're going to take that event delta, represented as an NNF, as I showed you earlier, that satisfies 2 properties. The first property says anytime you have an OR between 2 events, I want these events to be mutually exclusive. Anytime you have an AND between 2 events, I want these 2 events not to share variables. NNFs that satisfy these 2 properties are known as deterministic decomposable NNFs, and they have this acronym. This is a universal representation. I can take any event and put it in this form. And if you do, and under this assumption, now you can compute the probability of the event in linear time. But the 2 caveats is this assumption, which we know does not hold usually, and that we need to have the probabilities of these individual literals, which we also don't have individually. We're going to take care of that shortly. But this should not be surprising, because as we know from probability theory, that the probability of a disjunction can be broken like this if the events are mutually exclusive. That's not true in general. And the probability of a conjunction can be decomposed like this if alpha and beta are independent, which is in this case ensured by decomposability and this assumption that we made here. Let's look at the visualization first before we relax these assumptions. This is a distribution that satisfies the assumption. It was induced by these probabilities of literals. This is the positive literal L, negative literal L. So if you take an atomic event like this one before last, its probability is obtained by multiplying these probabilities of literals. And we're interested in the probability of this event, which happens to be this. So if you add up these 9 probabilities, the probabilities of the 9 atomic events, you will get this number here. So what we're going to do is we're going to take that event, represent it as a negation normal form that is both deterministic and decomposable. You can verify that this NNF satisfies these properties. For example, here's an OR. This and that are mutually exclusive. Here's an AND. The variables appearing here do not overlap with the variables appearing there, and so on. Now, how do we compute the probability? Just like was suggested on the previous slide. You start with the probabilities of the literals, and you move up multiplying at and doing additions at ORs. And if you do that, you get this particular probability, which is what we want. Now, we did this under strong assumptions that do not hold. We're going to relax these assumptions, but the final picture is going to look precisely like what you're seeing now. That is the probabilistic reasoning systems that we'll come up with. We'll end up building events as circuits, and probabilistic reasoning will be linear time feed-forward propagation, just like in neural networks. Now, to relax the assumptions, I need to tell you about one more great insight on the next slide, which shows that this can be done in a more general setting. What is this more general setting? Instead of working with probabilities, we're going to work with weights of atomic events. These weights are non-negative numbers. Unlike probabilities, they don't have to be between 0 and 1. And unlike probabilities, they don't have to add up to 1. And they are induced by having weights on literals that are also non-negative numbers. So if you look at this atomic event, the weight that it has is simply the product of the weights of the corresponding literals. And now the story is that I have an event, same event, but I want to compute its weight. by adding up the weights of its atomic events. And in this case, it happens to be this. Now, you would think that we can just immediately do it in the same fashion by representing the event as an NNF that's deterministic and decomposable. Not exactly. We need one more property. Why? Because in probabilities, the probability of a literal and its negation have to add up to 1. Here, there's no relation between the weight of a literal and the weight of its negation. So we just need one more property, and that property is called smoothness. Anytime I have two events with an or between them, I want the two events to mention the same set of variables, and that does not hold here. So if you look here, for example, here I have P, and here I have P and A. It's not the same set of variables. We can easily make this NNF smooth by just adding some redundant parts. So by replacing these three literals by equivalent parts, like here, so here I had L, and now I have L and K or not K, this is now smooth. All right. Now I have to say, decomposability and determinism are properties that are hard to enforce, in the sense that if you give me an NNF that's not decomposable and say make it decomposable, I can always do that, but its size may blow up. Similarly for determinism, not smoothness. Smoothness can always be enforced in polynomial, actually quadratic time, and the size will only grow quadratically. But now that we have smooth, deterministic, decomposable NNF, I can compute the weight of the formula as we've seen before. I will add at or nodes, and I will multiply it at nodes, and basically that's what we have. Okay, now we have a couple of more insights, and you'll get to see what revolutionized this area and what gives rise to state-of-the-art systems in probabilistic reasoning, and realize that we're all in the world of logic and what logic tells us about events. The key step that is missing is we have to get rid of that assumption about variables being independent, because that does not hold. And the key to doing that is to introduce auxiliary variables. And we're going to do this in a particular context, in the context of Bayesian networks, because we have to work with distribution that does not satisfy that assumption. A Bayesian network is a graph like this, and what you need to do is, for variables that are root nodes, you have to give a distribution over these root nodes. So here's the distribution over A, probability of A being false, probability of A being true. For variables that have parents, you need to give conditional distributions for the variable, conditional on the states of the parent. So the parent has two states, so I need two distributions, one conditioned on A being false and one conditioned on A being true, and similarly here. This Bayesian network specifies a joint distribution over all atomic events, and here's how it looks. Now, why this distribution doesn't matter, but what matters for this discussion is that the probabilities of the individual atomic events are very clear to see how they are computed. Each one of them is 3 parameters. By the way, these numbers are called parameters. So there's 3 parameters. One comes from this table, one comes from this table, one comes from that table. Which one do you pick from each one of these tables? The obvious way. I picked this guy from this table because its subscript matches the setting of the variables here. Similarly for this, similarly for that. This distribution does not satisfy the independent assumption. But now we're going to see how we can compute probabilities with respect to it using what I just showed you. And as I said, the trick is to introduce auxiliary variables. For every parameter in the Bayesian network, I'm going to introduce 1 Boolean variable. So initially I had 3 Boolean variables, A, B, C. Now I'm going to have 13 because I added 10 more. And now we're going to be operating in a bigger space. Initially we had only 8 atomic events. Now we were going to have 2 to the 13 atomic events, but we're going to be only interested in 8 of these atomic events, the ones that in a way correspond to the original atomic events of the distribution that we're trying to do a computation with respect to. Now, what are these atomic events? So this part of them is clear. What are these? It's very simple. These additional variables are split into 3 groups, depending on which variable generated them. For each group, we're going to turn exactly one on and all of the others off. Which ones will be turned on? We will do that based on what parameters participated in the probability of that event. So since here we have A false, we're going to turn this guy on and this is off. And given that we have this, we're going to turn this guy on and all of these off and so on. So this is our first atomic event that we're interested in, and similarly for the others. Now, you're going to tell me, how are you going to get a formula that specifies this particular event? Next slide, very easy. We can do that in linear time. But look what happens now. Now, you'll basically see the final insight that will lead to the state-of-the-art systems. We're going to set the weights of these variables, the original ones and the auxiliary ones. And the weights are as follows. For any positive literal of these auxiliary variables, like this, this, and that, the weight is simply the corresponding probability, and all other weights are 1. Now, let's see what happens as far as the weight of a particular atomic event like this one. In this case, the weight of this atomic event is the product of 13 weights, 1 weight for each literal. But given how we set weights, only 3 of them will have weights that are not 1. So this weight is effectively this. All of the other 10 weights are just 1. And this product is simply that, which is exactly the probability of that atomic event. So now we emulated the original distribution in which variables are not independent by a distribution of weights where the variables are independent. And now we're going to do what we showed you earlier, but on that. What we need now is this event as a formula, and that actually can be done very easily. I'm going to just show it to you, and you can see for yourself. This formula that you're seeing on the screen specifies that particular event, and it can be written in linear time. Basically, every auxiliary variable generates a subformula in the obvious way. Look at the subscripts and look what appears here. Look at the subscript, look what appears here. So now the approach is, you take the Bayesian network, you spit out this formula, and you represent this formula or the event of that formula as a smooth deterministic decomposable NNF. And now you can do inference in time linear in the size of this structure of the event. As you've seen, what we've done is we've been multiplying at end nodes, we've been adding at OR nodes, we've been replacing these variables by their corresponding weights. These are all of the other variables. Their weights should be 1, but I'm going to keep them in symbolic form. So after we get this formula from the probabilistic model, compile it into this structure, and do these substitutions, we see this. And that is what we will be using for probabilistic reasoning. We know the values of these weights. We know the values of these weights. Why did I keep them in symbolic form? Because if you simply evaluate the circuit, you're going to get 1 at the top, because you'll be adding the probabilities of all of the atomic events. But that's not what we're interested in. We're interested in computing a probability like this one. What's the probability that A is true and B is false? And that can be done now easily by just adjusting weights. If you use these weights here, what's going to happen is any atomic event in which A is false will end up getting a 0 weight. Any atomic event in which B is true will end up getting a 0 weight. So they will be basically thrown out. That's exactly what you want. So if you do that here and push the numbers, you're going to get the probability of this event. That, my dear friend, is the state of the art. And this creature that you're seeing in the screen is known as arithmetic circuit. It's a creature of its own. I introduced it in this fashion to show you the role of logic as the calculus of event in producing it. It can be motivated completely differently. There is a whole community, actually multiple communities in machine learning that are dedicated to this creature, pursuing it sometimes under different brand names, like some product networks and probabilistic circuits. As I mentioned, this is what the state-of-the-art system, ACE embeds these techniques, but I have to warn you that the performance of ACE that you're seeing is based on not exactly what I just told you, but later versions of this game, more sophisticated. This is the paper that has kind of state-of-the-art encodings that ACE is based on, and still state-of-the-art. we found that people are using these in way much more broader settings that we anticipated initially. I see a lot of papers about quantum simulations these days. Don't ask me about the details, I don't understand them. But given the interest and given how how the user base has grown over the years, Mark Shavira, who did his thesis on this subject and produced ACE, he's the main co-author, and I sat together a few months ago, and we're working now on version 4. It should come out any minute. So there will be an updated version of ACE coming up soon. And I'm going to go now to machine learning to say a couple of words. But I just want to tell you that there's a lot more on this aspect as far as structuring events in a particular way to facilitate computation. And just to give you a glimpse of that, what I told you about computing probabilities of events by adjusting weights, that only works for simple events. If you want to compute the probability of an arbitrary event, that doesn't work. And to be able to do that, what you really want is you want this event, which is an intersection between what you want to compute and the event that we talked about that led us to this. You want to get this conjunction as in this form. And that's not easy, even if each one of these is in that form. So there are further properties that you can impose that allow you to do this conjunction efficiently. And one of them is called structured decomposability. There is another one called partition determinism. Both of these are stronger versions of decomposability and determinism. You put these together, you get yet another NNF structure that's been quite influential, known as SDD. And a variant on it is, or a derivative of it is called probabilistic SDD, and so on. So there's a lot of these additional properties that you can put on events. And here's an example of why you would want to do that. But there are many other things that can be done with these additional properties. So now let me just say a couple of things on machine learning. And here you see something very interesting. A classical problem in machine learning is this. Let's say you have a Bayesian network. And here it represents, you have a disease and 2 symptoms, but you don't know the parameters. You don't know the numbers. So you want to learn them. And in machine learning, people talk about data sets. You learn from data sets. So they make a distinction between a complete data set and an incomplete data set. So what are those? Here's a complete data set. Every row is an example. Think of it as a patient. So this is saying I have a patient, does not have the disease, does not have the first symptom, does have the second symptom, and so on. An incomplete data set is when you don't know everything about the patient. So here I say, okay, I know they do not have the disease. I know they have the second symptom, but I have no idea whether they have the first symptom or not. The people make the distinction between these 2 types of data sets because this one, even though it does not appear in practice a lot, is very well behaved computation and statistically. Now, but look carefully. Okay, this is profound. What is an example? In this case, an example is nothing but an atomic event. And what is an example in this case? An example is nothing but a simple event. Now, what prohibits us from having a data set in which examples are arbitrary events like we're seeing here? You will not see this in the mainstream literature. Now, you're going to tell me, what does this mean? Well, I'll tell you what it means. Here, I told you I know everything about the patient. Here, I told you I know they did not have the disease, but they had the symptoms. I have no idea what's happening. And look what this is telling you. This is telling you, I know the patient had the disease. I know they had symptoms, but I don't know which symptoms. They may have had both of them or one of them. And if it's one of them, I don't know which. Very meaningful. The second one says, I don't know if the patient has the disease or not, but I know they had exactly one symptom, but I don't know what that symptom is. In the next slide, I'm going to show you something that's even more convincing as far as, now, why do you not see these kind of data sets in machine learning, which are very meaningful and can be very powerful? The main method for learning parameters is to try to optimize this quantity. What is that? Let's say theta is a vector of 10 numbers, the numbers you're trying to learn. What this is doing is you plug in these numbers here, and therefore you get a distribution. So you compute the probabilities of the examples and take the product. You can think of this as the probability of seeing that particular population of patients. And what you want to do is you want to choose your parameters to make this as high as possible, to maximize the value. Now, to compute this, you have to compute probabilities of events. In this case, I'm computing probabilities of atomic events. In this case, I'm computing probabilities of simple events. That's bread and butter for machine learning and probabilistic reasoning. You'll find chapters dedicated to this in these books. In this case, I have to compute probabilities of arbitrary events. That's not part of the repertoire. You can find books that are this thick on the subject, and you will not have any treatment of computing arbitrary events. If you look at the main algorithm, or one of the main algorithms for learning parameters, it's called the EM algorithm, not just in Bayesian networks more broadly. And what this algorithm does, it takes initially some initial set of parameters, usually arbitrary or random, and then keeps revising them with the guarantee that every time I update my parameters, this quantity will never decrease. It either increases or stays the same. To give you this guarantee, the update equations end up computing probabilities like this, where you are conditioning on events. The algorithm works, whether these events are atomic, simple, or arbitrary events, but it was never applied in this, because again, you have to compute probabilities of arbitrary events, which is not part of the repertoire. This is a case study that concerned a type of distributions people call preference distributions. People want distributions that tell me how people behave. And one type of preferences are total orders. So this is an actual data set that people use in the literature, about 10 items of sushi. And you want to know how people order them, their preferences. So this is an atomic event that tells me which is number 1, number 2, number 3. This is another atomic event. This is a huge space of atomic events. And I want to learn a distribution over these total orderings or rankings. What is a data set in this case? A complete one looks like this. You give people questionnaires and you tell them, tell me what's your number 1, number 2, number 3. If they want to have an incomplete one, you get this, where someone will tell you, okay, I can tell you what is my number 1, sushi number 2, but I'm not telling you what my number 3. That's as far as it gets. What is an incomplete data set in the sense that we talked about, where if you're allowed to use arbitrary events to specify examples, you can do this. A user can come and tell you, all I'm telling you is I prefer fatty tuna over sea urchin, and I prefer tuna over sea eel, and that's all I'm telling you about myself. I don't want to tell you anything. And so on. You see how powerful? All right. Now we know how to do this systematically, how to learn from these kind of data set. In fact, this paper proposed an EM algorithm that operates on these data sets. So I'm done with my first part of the talk, and I hope now you see the 3 first ingredients of this logic as a calculus of events. One dimension of this calculus is about the structure of events as determined by various properties, and there's more. Another dimension of this calculus is what is enabled by various structures. What can be done efficiently on these structures? And I showed you some examples of that. The third dimension, which we didn't talk at all about, is how do I enforce these structures? How do I take a formula and make sure that the event it specifies is structured in a certain manner? That's known as knowledge compilation. Everything I talked about so far can be viewed as a reframing of a story that has been evolving over the last 20 years or so under 2 common labels that many of you probably have heard of: the label of tractable circuits and the label of knowledge compilation. In fact, the main paper that's associated, historic paper associated with these labels, is this one that I wrote with Pierre Marquis. This paper actually is dedicated to the second dimension of this calculus. By the way, this paper did not introduce any structures. It studied structures and showed what is enabled by various structures. These properties that lead to these structures, these 3 were introduced before this paper, the rest came after. So the paper is the most comprehensive historic reference, but it's outdated, of course, because a lot more structure came after that. And now we're going to go to the second part of the talk, where we're going to add the 4th dimension that many of you probably have never seen before, where we're going to talk about event abstractions and see what logic as a calculus of events tells us about abstracting events and how that will play a role in explainable AI. And I will tell you, prepare to be amused. Let's get started on explainable AI. Let's see. Okay, I'm doing great on time. That's my plan. In explainable AI, there are 2 questions that pretty much most of the literature of the 5 to 7 years have been focused on. I will show them to you intuitively using a concrete example next, and I'll tell you how. By introducing one abstraction operator that takes an event and abstracts it to another event, we can make an account of what's going on there, and you see the consequence of that. Quite interesting consequences. The two types of explanations are this, and we'll illustrate them with a decision graph classifier. Doesn't have to be. It could be neural network classifier, Bayesian network classifier, random forest, but these guys are friendly for visualization. So this is a classifier that is meant to decide whether to admit or reject an applicant into a program based on their SAT score, GPA, essay, and interview. Here's an applicant that is called an instance in this case, which happens to be an atomic event. SAT score, GPA, essay. This classifier says reject them. And now the first question is, why did you make this decision? And the answer to this is known under different names. I'm going to use the name sufficient reason. And here we have two sufficient reasons that explain why did you make this decision. The first one, for example, says the reason this person was rejected because they failed the interview and the essay. What does that mean? That means doesn't matter what their GPA is, doesn't matter what their SAT score is, guaranteed. Just because they failed the essay and the interview, they will be rejected. You can check that for yourself and you'll find out. Here's the second sufficient reason, which says this is another reason why the person was rejected, which means their essay didn't matter. Even if they actually succeeded, that they will still be rejected. The second question is, what does it take to change the decision? How can I minimally change the application so that the person is accepted? And the answer, again, is not under different names. For now, I'm going to use necessary reason. What are these? Each one of them is a minimal property that is satisfied by the instance. But if you break that property, then you're guaranteed that the decision will flip. There is only one way to break the first property in this case, is by setting interview to pass. Guaranteed, if you do that, this applicant will indeed be admitted. There's only one way to break this property, by setting these variables this way. Guaranteed, the applicant will be admitted. In the third case, because GPA has multiple values, there's two ways in which you can break this property. One of them will flip the decision, the other does not. If there are multiple ways to break the property, you're guaranteed at least one of them will flip the decision, but not necessarily all. If all the variables in the necessary reasons are binary, then there is only one way to break it, and that way is guaranteed to flip the decision. Now, the next slide, pay attention, all right? Because here's what's going to happen. Dozens and dozens of papers have been written about these guys, how to compute them for this and that type of classifier and so on. And look now in one slide and one abstraction operator that'll show you what's going on. Just before that, another example of sufficient reasons from neural networks. This was a neural network that is looking at images, deciding whether there is 0 or 1. It looked at this image and it said it is 0 correctly. It says, what is the sufficient reason for that? And it was these 3 pixels. What does that mean? As long as these 3 pixels are white, you can do whatever you want with all of the other pixels. And I guarantee you this neural network will label this image as a 0, including this one. All right? This was done based on the techniques that I'm mentioning here that appear in this paper. Okay, now please pay attention to this part. We have a few more slides, penetrating slides though. Events in explainable AI. First, I hope you know by now that the notion of an instance, which is the input to the classifier, is an event, and it's actually an atomic event. Now, the classes are also events, because what is a classifier? A classifier is nothing but a partitioning of the instances into groups, into classes, right? That's what a classifier is. And therefore, each class, which is an event, can be specified by a formula. We call these class formulas. So if you actually give me these class formulas, where each formula characterizes the instances in a particular class, as you see, we're done. Now, this is the most fundamental, profound notion on which we will have the next few slides. Take an instance in a particular class, like the one we looked at. There is an event, a special type of event, that includes this instance, and that's included in the class. We're going to give it an A. This event can be viewed as an abstraction of this instance. If you get a hold of this event, you can compute necessary and sufficient reasons from it. You'll be done. And this story is independent of the classifier. And moreover, this event, which we're going to call the complete reason for why this instance belongs to the class, can be obtained very elegantly using a logical operator that I'll show you later. You take this operator, you apply it to the instance, and apply it to the class of that instance, and you get this event that is shown here. And once you have it, you're done. Not only can you get the sufficient and necessary reasons, you can do many other things, but we won't be able to talk about this today. In particular, if you take this event and compute its prime implicants, you get the sufficient reasons. If you compute its prime implicates, you get the necessary reasons. If you don't know what these things are, you'll see visualization next. So one operator takes the instance as an event, the class it belongs to as an event, gives you another event. That's it. You have the two types of explanations that dozens and dozens of papers have been written on. But you see the consequences of seeing it this way. Because, by the way, these notions of sufficient and necessary reasons were introduced originally before this event was known. Here's the visualization of this complete reason for the example we looked at. That would be the complete reason for the applicant that was rejected. I'll tell you how you get this guy. But here are the sufficient reasons, which happen to be the prime implicants of this formula. And here are the necessary reasons that happen to be the prime implicants of this formula. Now, if you don't know what these things are, just think this. If you take these two guys and put them in an OR, you get an event that's equivalent to that. If you take these three guys and put them in an AND, the first and the second and the third, you get also an event that's equivalent to that. So this, and that are all equivalent. That means the sufficient reasons are simply a rewrite of the complete reason in a particular syntactic form. And the necessary reasons are just a rewrite of the complete reason according to a syntactic form. These forms, engineers like to call them minimized sum of products and minimized product of sums. They have been studied in computer science for over 50 years. So the complete reason, the disjunction of sufficient reasons, the conjunction of the necessary are all the same event. This was introduced in this paper from my group and is viewed as the paper that kicked off and started this area of formal explainable AI. This notion, in a more general version of it called contrastive explanation, was proposed here. It was popularized in AI by this paper, and the treatment I'm giving here is based on this paper. What I want to show you now is just two more things, and we go to the final parts of the talk. First, how do you compute this complete reason? What does it represent? How do you compute it using this operator? Because this operator and the machinery that comes with it is this fourth dimension of the calculus of events. And then I'll give you two key consequences of this view of what's going on here from the lens of logic as a calculus of events. The complete reason that I just showed you for this instance, I'm going to describe it intuitively, and then I'll tell you the operator that gets to you. Here's how you get it, because it's an abstraction of the instance that tells you why this instance belongs to the class. You start with the literals that appear in the instance, and you combine them using ands and ors. If you do that, anything you get will be satisfied by this instance, so can be viewed as a description. But what I want is two conditions on this. I want it to still imply the class formula, the reject formula, and I want it to be the weakest such NNF that has these properties. So the complete reason for why the instance was rejected is the weakest NNF whose literals are in the instance and that satisfy this property. So you can think of this effectively as a necessary and sufficient condition of why this instance belongs to the class, right? Now, I'm going to show you the operator that gets you this. But remember, the operator applies to the instance and the class formula, and I have not shown you any class formula. So let's visualize a couple of them. Here's a naive-based classifier that looks at patients based on their blood tests and Canning tests and classify them as either pregnant or not. So the way it works is you set the values of these variables, you compute the property of pregnancy, you check against the threshold, and if it's above the threshold, you say it's yes, otherwise no. So there's only two classes. This is a binary classifier, two classes, and therefore two class formulas, and here they are. There's only 8 instances in this case, which correspond to the settings of these variables, and 5 of them turn out to be positive, 3 negative. This formula captures the 5 positive instances. This captures the 3 negative. You give me these two formulas, I'm done. Anytime you give me an instance, I can compute its complete reason using the operator I'm going to show you next. And then from that, you can get sufficient and necessary reasons. You're going to tell me, where do you get these class formulas from? We have algorithms to do that. That takes this classifier and spits out these class formulas. I'm going to give you a pointer later. Here's another classifier in the form of decision graph. Here we have two variations. First, the variables are not binary. Each one of these variables is ternary, has 3 values. And I have 3 classes, 1, 2, and 3. So I have 3 class formulas in this case, and here they are. Now, here we're operating in a discrete setting. These literals are specified differently now. This literal says the variable x has the value 1 or 2. Otherwise, everything is the same. There are 20 instances in the first class, 3 instances, and 4 instances in the last class. Again, once I have these class formulas, you'll see in the next operator how I can compute complete reasons and therefore the answers to the 2 main questions that have been occupying the attention of a whole community over the last 5 to 7 years. Let's do the operator, the abstraction operator, and prepare to be surprised. First of all, by the way, the notion of a complete reason was introduced earlier, and later we found out in this paper how to compute it using this abstraction operator. Here's the operator. It applies actually to a state of a variable and a formula. This is the event, and gives you another event. What is this? Take the formula, fix the value of the variable x to true everywhere in the formula. And this says, take the formula, fix the value of the variable to false everywhere in the formula. Here we applied it to a positive state of a variable. You can apply it to a negative state of a variable. This operator is commutative. You can apply it to multiple states of multiple variables in any orders, and you'll always get the same event as a result. In particular, if you apply it to the positive and negative states of a variable x, in any order, you're going to get this. Some of you may know this. This is actually the universal elimination of variable x, which has been in computer science forever. In fact, it appears in Boole's book from the 1800s. He used this as a technique for conducting proofs. Now, we're going to use it now to compute the complete reason. How? Here's the instance, which is the set of variable settings. Here's the class formula of the instance. The complete reason is nothing but you apply the operator to every state here in any order you want. And this is the compact notation for that. This is the abstraction of the instance, the event that I showed you there that includes the instance as included in the class and that holds the secret for answering these questions. And guess what? This operator is very well behaved. It distributes over conjunctions and it distributes over disjunctions if the disjuncts do not share variables. If we have this property that anytime you have something or something, these 2 guys do not share variables, we're going to call this or decomposability, yet another property. Now, what this result tells you, if you're able to get your class formulas in the form of an or decomposable NNF, then computing complete reasons can be done in linear time. And for a certain type of classifiers like decision trees and decision graph under the test once property, you can indeed easily get class formulas in this form. You can imagine the implications of this computation. But let me close with a couple of consequences, all right, on this, and then go to my concluding slide, because this is very substantial. I have an example of this. I'm going to skip it. Okay, I told you earlier that necessary reasons are a special case of something called contrastive explanations. Contrastive explanations were introduced quite early. And here what they are. And people have a hard time implementing true contrastive explanations. They implement necessary reasons, and sometimes they call them contrastive explanations. The 2 notions of a necessary reason and a contrastive explanation collide into each other only when you have binary classifiers. If you have multiple classes, they're different. Let me explain. Suppose you have a classifier that decides whether an applicant is approved for a large loan, small loan, or declined. So we have 3 classes. And now you have an applicant that has been approved for a small loan. So it sits in the 2nd class. A contrastive explanation asks the following question, as originally proposed. Why was this person approved for a small loan as opposed to a large loan? And the answer to this tells you how we can modify the application so that this person will get a large loan instead of small loan. Necessary reasons do not do that. Necessary reasons just tell you how to modify the instance to kick it out of the small loan, but it gives you no guarantee on whether it's going to go into the large loan or the decline. People want to implement true contrastive explanation. That's not easy. And the proposals you see out there are relatively complicated and specific to certain classifiers. Let's see how you can do this in one line, given our new understanding of what's going on here through abstraction. Well, it's very simple. You merge these two classes, the small loan and the decline. So now I have a binary classifier. The first class is a large loan, and the second class is small or decline. My applicant is clearly now is in this new merged class. If I know how to kick it out of this bigger class now, I'm guaranteed that it will land in this large loan class, which is what I want. And we know how to do that using necessary reasons. So instead of computing the complete reason for this class, you compute the complete reason with respect to the merged class. And the prime implicates of that, which are the necessary reason, will now suggest minimal ways in which you can modify this instance so that you can ensure that this person will get a large loan. This technique that I just mentioned appeared in this paper. And just to give you a sense of how big this picture is and how big the story is, I'm going to end with one further consequence. This is a problem we noticed in 2020. We put it in a paper that was rejected by a major conference. We put it on the archive, and we've been trying to chase this problem for the last few years, and we finally figured it out. The observation we had from a few years back is that these explanations that I told you about, the necessary reasons and the sufficient reasons, as I explained them, are suboptimal. If you have discrete variables, they're not necessarily the right notions. They are the right notions for binary variables, but not when you have discrete variables. If you have discrete variables, we have shown recently, very recently, that you have even a better abstraction of the instance that we call the general reason, which is also an event, and that can also be computed by an abstraction operator. I didn't discuss it, but I will just give you a glimpse of the power this new event or this new abstraction gives you, and which was missed by the community. Now, we were the first in 2020 to allude to it. So there were some attempts to do something about it, but only recently the real first class solution came up to this problem. Let me illustrate it to you by an example of what it gives you. Here's, that's basically my last slide. Here's a classifier with discrete variables. Weight and blood type are discrete, and this is binary. So it's trying to classify patients as having certain disease or not. Rob is a patient, an instance, and it's classified as yes. And then you say, why? I'm going to just illustrate the sufficient reason. Why did Rob was classified as yes? If you use the existing theory and get sufficient reasons, you're going to find only one sufficient reason that says, because he has diabetes and his blood type is A. That effectively, that weight didn't matter, and that's it. Look what happens now if instead you compute this new abstraction and get its prime implicants. You're going to get two explanations. The first one says, actually, the reason why Rob was classified as yes is because he has diabetes and his blood type is not one of these two. It's not about being A. It's about not being one of these two, meaning it could have been B and it would still be classified as yes. This is more informative. Now, you're going to get another one, another explanation in this case, that the reason why Rob was classified as yes, because he has diabetes, his weight is not normal, and his blood type is not O. It didn't have to be under. It had to be not normal. So it could have been under or over. It didn't have to be A. It just had to be not O. So that leaves three possibilities. You can write these formula like this. These are more informative about the instance, about the classifier than this, and you get them by operating with this more general abstraction that's called the general reason. We call these general sufficient reasons. You can read about these in this recent paper. So Here's now, I promised you at the very beginning that by the end, we will have a clear definition of what I mean by the logic as a calculus of events. These are the 4 dimensions. Structures of events. It tells us about all kinds of structures of events through a set of properties, very nice and intuitive. The calculus tells us of what happens when your events are structured in a certain fashion. There is a computational arm to this calculus that tells you how to enforce these structures. And now we have this new dimension, which has to do with abstracting events, taking one event that belongs to another and tell me why is it in that bigger event? What does it take to keep it there? What does it take to kick it out of there? And I hope you have seen the implications. Some pointers. I talked about explainable life for 20 minutes. If you want to hear a 2-hour tutorial, I gave one last summer at the Symposium on Logic and Computer Science, available on YouTube. There is a paper associated with that. It's available on the archive. If you want to hear more about the story of knowledge compilation and interactable circuits, that's the first 3 dimensions of the calculus. There's a 2-hour tutorial I gave at the Simon Institute. And recently I wrote what's perhaps the most comprehensive and up-to-date tutorial / survey on the subject. It appeared in this book. It's also available on the archive. And if you really have time and you want to dig into, you can check my graduate course on the subject. Stefan mentioned that apparently students look at it, which is great. And I will leave you with my final messages so that you can read them at your own leisure. I am done here, and I'm happy to take any questions. Thank you.
Thank you very much, Adnan. This was very wide span you covered, and I think it was also most of the questions start with an appreciation, amazing work, thanks for the great talk, etc. So I would like to remind participants to still add their questions and vote for some of the questions already there. And I think, Agatha, you will read the top question.
Let's start with the top question that, of course, start with amazing work, where I fully agree. Okay, I would like to hear you about making this kind of model richer. From an ontological viewpoint, what you call events are actually types of events with an assigned probability or weight, and that can be instantiated by multiple instance events. That's one thing. The second thing is that ontologically, events depend on property of objects. In other words, events are a way of speaking about objects in action due to their capabilities. Once we add this ontological feature to this form of modeling, what would we get?
What was the last? Just repeat the very last part, the very last sentence.
Once we add these ontological features to this form of modeling, what would we get?
I don't know, but let me tell you, here's the thing. I hope that someone will explore this. Let me tell you what is implicit in this talk. Please, let's stop talking about logic as a tool, as only a tool for representing categorical beliefs, that we use it to represent facts and then what follows from these facts. It's a lot more than that. Everything. Did you hear me anywhere in this talk about a knowledge base and what follows from the knowledge base? No. There was even, that's not be a part of discussion. It's what does it tell us about events. So I talked about one type of events in a very restricted setting, propositional or discrete, and look how far we've gone. If someone wants to talk about events in a broader setting, from an ontological point of view, and draw a parallel picture, please do it. In fact, we need to do that. One of the main messages is we need to crystallize this understanding of logic and develop it further from this point of view, because you can see how rewarding that is. And it is not in competition with probability, that this is about facts, this is about numbers. This is an old story. It's not in competition with machine learning in the sense that one is rigid, one is flexible. It is in the heart of all of these things. So if you want to pursue broader settings, like what was suggested by the question here, I think that's what we should do. because that's where we have even more influence and more progress. I just spotted one of the questions in the talk that's saying, since probabilistic reasoning is the sharp P hard, that means these circuits can blow up sometimes. Indeed, of course. And the question is, are there situations where you can guarantee me? Of course, yes. There's quite a bit of literature on situations where I guarantee you that the circuit will not blow up. Check my book chapter, the one I mentioned about tractable Boolean and arithmetic circuits. You will it's basically summarized what happened over the last 25 years, and you'll see pointers to a lot of these results, including ones about complexity. In fact, there's, just to give you a sense of how big this is, we even now know how to represent these circuits using tensor graphs, just like people do in neural networks, because actually they can get really big. I was able to compile on my laptop, Mac laptop, it's powerful, but still a laptop, up to 1 billion nodes in these circuits that can be processed very efficiently if you represent them as tensor graphs, because the inference is just linear, feed forward, just like neural networks. So you'll see in that book chapter some references to papers where people looked at, even there's an area in which people come up with dedicated hardware for these circuits. I was involved in one of these works with a colleague, Jason Kang here, who's an expert in this area, So you build custom hardware to actually evaluate these circuits because they're just feed forward, just like neural networks. So.
Okay. You answered the second question. The third question.
Okay, the third question is, can you also handle other uncertainty measures like Dempsey-Schaeffer belief functions, possibility measures, or ordinal belief measures with your approach?
So that's a good question. I think these needs to be checked one by one. You realize that it's not just probability measure, but we did the weights, right? So the weights is more general. So I think, I mean, roughly some of these will, some of them maybe not. I don't know about Dempsey-Schaeffer. I worked on this long time ago. Maybe not, but that's another great thing to check out. And if not immediately based on what I mentioned, maybe some modifications, maybe some new structures or events will allow that. And then we'll grow the calculus even further. But I think possibility, probably yes. Possibility, I think almost sure that it can be done. I don't know about Dempsey-Schaeffer.
Okay, then there is something, I'm not sure whether it's a question or just a statement. It's a brief statement that the complete reasoning is in a way grounding in events. I don't know, can you make sense of this?
The complete reason is in a way grounding in events. Let me show one slide, and I think maybe this person is alluding to that. Okay, look at this. The complete reason is referring to the complete reason, or she's referring to the complete reason. This is an instance. This is the class of that instance. Now, I don't want you to think about now an instance and a class. Think about an atomic event and an event that includes a bunch of atomic ones, including this one. So this satisfies that. Here's the complete reason, okay? It is an abstraction of this atomic event that tells us, why does this satisfy that? Now, if you compute the sufficient reason and necessary reason, like what they're telling you, this is telling you, what does it take to keep this as satisfying this? It's telling you, if you keep this and that fixed, you can change this any way you want, and this guy will still satisfy that. Similarly, this guy says, if you keep this and that, you can change this any way you want, and this will continue to satisfy that. Now, look what this tells you. It tells you, you can change only this, and then you can make this to stop satisfying that, or this atomic event to belong to that. That's one way to kick this atomic event out of the circle. You can do that by only changing this. And this says, you can also do it by only changing these two things. So you want to think about it as instance in a class, or think of it as an atomic event satisfying a bigger event. And this abstraction operator is really studying the implication relation. And maybe that's what's meant by grounding here. It's beautiful, it's remarkable. And that it actually again, explains in such a succinct and mathematically elegant way a whole area in explainable AI. By the way, I should mention that the thing that I presented is the Boolean version, which is in this paper. This paper actually at the very end, in the last paragraph, said, this abstraction operator can be generalized to discrete variables, and here's the suggested generalization. But it is this paper that went and studied that in detail. And what you're seeing here is the discrete version of that abstraction operator.
So there is a question that probably most of the logicians would like to ask, namely, how about first order logic?
Aha, I'm glad someone asked this. I would love to see that. See, just for historical to mention, I grew up at Stanford at the time when almost every other course was first order logic. So I took probably a dozen of these, and I always look at the current state of affairs, and I realized the interest in this subject is diminishing. And it has, because I think people are still glued to the old perceptions about what is this meant to do, that you represent beliefs as first orders, and then you look at implications through resolution and so on. And I hope what I did here suggests that, no, you can use such beautiful machinery in way more broader contexts. So by all means, I think people should be looking at employing first order logic in a similar way that was done here, so that the logic as a calculus of events goes beyond the propositional and discrete settings that I talked about. I don't have a lot to say about that, but I hope others will, and soon.
And how does this calculus of events relate to the notion of handling events that happen over time, as addressed in temporal logic?
So that's a good question. You know, I was preparing the talk. I suddenly remembered a title of a paper, I think by McCarthy and Pat Hayes from the old days. It's called Event Calculus. And it was about this. It's about that, events over time. Same story. This is a static setting. You can imagine doing something similar in a more dynamic setting. You look at problems that involve time, and you inject what we know about the calculus of events that I discussed in those settings. Again, work. Please, main message is, let's broaden our view and messaging on what logic is and what logic is not, what logic can do, what logic cannot. We are not being served here by the stories that are still being told in major textbooks on AI about what logic is and what role it plays. It's still the story I told you on the first slide, and it's misleading. It's not fair to this fantastic machinery to box it in this fashion. It is significantly and more useful than what that may suggest. I think I just saw a question pop up about, can you take advantage of SAT solvers? Indeed, that happens in the third element of that calculus, where we try to take formulas or specifications of events that do not satisfy the properties, and we want to convert them into formulas that satisfy. SAT technology is at the core of that. Just to let you know, perhaps the best compiler out there, or one of the best compilers out there, for compiling formulas into ones that are decomposable, deterministic, and smooth, is the CTD compiler from my group, which ACE uses. And I wrote that in C a while back. A new version is coming up. And the first layer of that compiler is a SAT solver. It uses that solver critically in enforcing these properties. Now, we did not talk about that subject at all today, but I gave you pointers to that. Absolutely.
Okay, and then there's a question whether one can reverse engineer a neural network, because neurons could also be considered as atomic events, and so to reverse engineer this and leading that to structures of interest logically, kind of getting, I guess, a logical explanation of a neural network.
Possibly. I think for this person who asked this question, here's what I would recommend. Somewhere there, when I showed that picture about the 0 versus 1 and neural network, check that citation. Not that citation. In that paper, there is a reference to an earlier workshop paper on the same subject. You will find that we were able to go into each neuron, not just the final input-output, but each neuron, and use these techniques to tell you what each neuron is actually doing. And one thing that we found out, that a lot of the neurons are redundant. You can take them out and nothing happens to the neural network. Input-output is still exactly the same. So these techniques were actually used not only to reason about the input-output behavior, here's the input, here's the class, but really what's happening inside. So that may be along the lines you're asking about. So check it out. The paper itself, which is in KR, but the workshop version, which had a lot more empirical results.
Okay, so there are no further questions in the chat, so I think we can come to an end. Maybe at the very end, it's very difficult these days to have an event and not mentioning large language models. I don't want to open a Pandora's box, but maybe if you can say 2 sentences about what the role of logic and reasoning could play now in view of this new large language models.
I mean, I think if you ask people, and I support this view, perhaps in these kind of setups, what people want to do mostly as far as using logic is to enforce certain behaviors. So you would want to use logic in the first sense. So you can use logic to represent constraints, to represent things that should not be violated. And you want, when you learn, to learn subject to knowledge, things that, no, I don't want you to mess around with because you may have the wrong data, but we know that these things should happen. And this is, in fact, one of the more interesting uses of this first role of logic. So you'll see people more broadly using these techniques actually to regularize neural networks. So when I'm training it, I'm like enforcing constraints. So just again, to not be misunderstood, the first role, the classical role, is significant and in this context very relevant, but it's not the only one.
Okay, yeah, thank you. That was again a very, I think, a great World Logic talk. The World Logic Day is coming in 2 days. Before we stop, I would also like to thank Andrea Hackel, who did the preparation and the organization for this event. Thank you very much.
No pleasure.
And of course, Adnan, for being available and also functioning as an ambassador of logic for our World Logic Day website. Thank you so much.
I have to tell you that ambassador title did impress my wife, so thank you. All right, guys, thank you very much.
Thank you, and happy World Logic Day, everybody.
All right, bye-bye.
Bye-bye.
So thanks everyone for joining, and I will now be ending this webinar. Bye.
Bye.